And welcome back. So we continue our cosmic journey looking at the moon. We of course had mentioned craters before, but let's go ahead and take a little bit more in-depth look at how those impact craters were very important in the formation and continued history of our moon. So the first thing we have to understand is volcanic versus impact origin of these craters. The moon provides an important benchmark for really understanding the history of our planetary system. If you recall, on Earth, this long history has been erased by our active geology, whereas on the moon, most of that impact history has been preserved. Until the middle of the 20th century, scientists did not generally recognize that the lunar craters were the result of impacts. Since impact craters are extremely rare on Earth, geologists did not expect them to be the major feature of lunar geology. The reason that since the craters we have on Earth are volcanic, the lunar craters must have a similar origin. So if we start examining volcanic and impact craters, we look at their profiles between the two of them, we'll see that they are quite different, as we can see in this picture here below. One of the first geologists to propose that lunar craters were the result of impacts was Grove K. Gilbert. He pointed out that the large lunar craters are larger and have different shapes from the known volcanic craters here on Earth. The only alternative to explaining the moon's craters was an impact origin. So what does it mean when we look at this? How does it become different? So we got to really kind of look at the cratering process itself to really understand how Gilbert was able to reach some of this conclusion. When a fast projectile strikes a planet, it penetrates 2 or 3 times its own diameter before stopping. During these few seconds, its energy of motion is transferred into a shock wave and into heat. The shock wave fractures the rock of the target, while the expanding silicate vapor generates an explosion like that of a bomb detonated at ground level. The size of the excavated crater depends primarily on the speed of the impact, but generally is 10 to 15 times the diameter of the projectile. So let's look at the stages in the formation of an impact crater. First thing is, the impact will occur. Then, the projectile will vaporize and a shockwave spreads through the lunar rock. Ejecta then are thrown out of the crater. And lastly, most of the ejected material falls back in to fill the crater, but some of it is found, of course, outside the crater in the form of an ejecta blanket. So, with that in mind, we can really then look at the impacts on the moon and really try and examine them. So an impact explosion has the central cavity being initially kind of a bowl-shaped thing, but the rebound of the crust of the moon partially fills it in, producing a flat floor and sometimes actually creating a centralized peak. Around the rim, landslides create a series of terraces. The rim of the crater then is turned up by the force of the explosion, so it rises above both the floor and the adjacent terrain. Surrounding the rim is an ejecta blanket consisting of material that was thrown out by the explosion. This debris then falls back to create a rough hilly region, typically about as wide as the crater diameter. Additionally, higher speed ejecta fall at greater distances from the crater, often digging small secondary craters where they strike the surface. And this allows us to then use crater counts. Remember, we could say crater counts are very important in looking at aging and stuff like that. So if a world has very little erosion or internal activity, it's possible to use that number of impact craters to really estimate the surface. And by age here in this context, we're referring to the time since a major disturbance occurred on that surface. Now, we cannot directly measure the rate at which craters are being formed on Earth and the Moon, since the average interval between large crater-forming impacts is longer than the entire span of human history. However, the cratering rate can be estimated from the number of craters on the lunar Maria, or calculated from the number of potential projectiles that are present in the solar system today. Now, both lines of reasoning can lead to the same estimations. So let's go ahead and do some calculating of crater impacts. For the moon, these calculations indicate that a crater 1 kilometer in diameter should be produced about every 200,000 years, a 10-kilometer crater every few million, and 1 or 2 100-kilometer craters every billion years. If the cratering rate has stayed the same, we can figure out how long it must have taken to make all the craters we see in the lunar Maria. Our calculations show that it is the age determined for the Maria from radioactive dating of return samples, 3.3 to 3.8 billion years ago. And so, because we have a match, it must be something that could be fairly accurate. The fact that these two calculations agree suggests the astronomers' original assumption was correct, that comets and asteroids in approximately their current numbers have been impacting planetary surfaces for billions of years. Now, one thing to keep in mind is, are these cratering rates over time consistent? Well, impact rates earlier than 3.8 billion years ago must have been a great deal higher, because remember, a lot of the data we have only goes up to about that 3.8 billion years ago. Now, when we compare the number of craters on the lunar highlands with those on the Maria, there are 10 times more craters on the highlands than on the similar area Maria. Now, radioactive dating of highland samples show that they're only a little older than that of the Maria. If the rate of impacts had been constant throughout the moon's history, the highlands would have had to be at least 10 times older and would have had to form long before the universe itself began, which doesn't make any sense. So, again, that means if we had, again, the same consistent rate, be super, super old. So, that means if we kind of look at this curve here, if we're looking at those highlands, the cratering maximum must have been a lot higher, because, again, we have so many more impacts that are present for our crater count.